Hello. In this video or these videos, I'm going to show some examples where I compute some triple integrals using cylindrical and spherical coordinates. And just for fun, I might also at least set up some of them with Cartesian coordinates as well. So the main running example here is going to be an example where we want to find a volume. So we're going to find the volume of the solid region D between the sphere x squared plus y squared plus z squared equals 3, the cylinder x squared plus y squared equals 1, and the plane z equals 0. So the first challenge is just to visualize and draw this. The plane z equals 0 is easy. It's the xy plane. For the sphere, we're going to take the top half of the sphere because we're cutting it at the equator anyway. So here's a sphere centered at the origin, and the sphere continues on below the xy plane, but we're not worried about that. And then we cut out a cylinder of radius 1, which is smaller than the radius of the sphere. So we imagine that we've drilled a hole through the axis of this sphere, and we're interested in finding the volume of this region D, which is sort of donut-shaped around that cylindrical hole. The sphere has radius square root 3, and the cylinder has radius 1. What's the height here? Well, the height at the north pole of the sphere would be root 3, but since we've drilled, the height at this point at the top of this cylinder is actually just a little bit lower. To figure that out, let's take a side view. So in a side view, the side view of a cylinder is just a rectangle. Of this radius 1 becomes half the width of the rectangle. We're looking for the height of this side. And what we know is that this corner point is a point on this sphere which has radius square root 3. And at that point, we can use Pythagorean theorem to find this height, and we get square root 2. So we find that the height of this point is square root 2. Now, let's try to find the volume. Just to see what happens, let's try in Cartesian coordinates. So on the xy plane, so taking a top view down towards the xy plane, we see that the hemisphere would look like a big circle, but we've drilled a little circle out of it. And in the xy plane, we're looking at this region, a ring or an annulus. It doesn't look very promising. It looks bad. It looks like a bad situation. Horizontal or vertical slicing. Let's say we go vertical slicing. And sure enough, we're going to have a bunch of different regions, maybe as many as 1, 2, 3, 4 regions. We could save some by using symmetry. We could just compute one quadrant. If all we're doing is computing volume, we could compute one quadrant and then multiply by 4. Let's do that. So let's take this quadrant and multiply by 4. So then we only have to deal with 1, 2 regions in the integral. So we can now describe this region by saying that, well, on each vertical slice, y ranges between the top of the outer circle and the top of the inner circle, which are circles of radius 1 and square root 3. And the first slice is when x is 0. And the last slice here is when x reaches the edge of the inner circle, so 1. Our second region has each slice still going to the top of the outer circle, but starting at 0. And the first slice is when x is 1, and the last slice is when x is root 3. Now, in our three-dimensional region, D, at any given point xy, the z value starts at z equals 0 and goes up until it hits the surface of the hemisphere. So 0 is less or equal z, less or equal square root 3 minus x squared minus y squared. So our volume is, well, we would have an integral for x from 0 to 1, an integral for y from square root 1 minus x squared to square root 3 minus x squared, and an integral for z from 0 to square root 3 minus x squared minus y squared. For the volume, we're integrating the function 1. Our volume element is dz, dy, dx. That's a volume element dv. And that took care of, that integral represents the volume captured by our first region. To this, we would add another integral for x going from 1 to root 3. This time y goes from 0 to square root 3 minus x squared. That's the difference. The interval for z stays the same, 0 up to square root 3 minus x squared minus y squared. The volume element stays the same, dz, dy, dx. And that captures the volume over our second region. These two integrals together capture all the volume over the first quadrant. So to capture all the volume, we better multiply by 4. Well, there. It doesn't look great. The first integral, the z integral, it's certainly easy to integrate, no problem there. But next thing you know, for the y integral, we're going to have square root 3 minus x squared minus y squared as the function that we have to integrate with respect to y. It's not going to be impossible, but it's messy. And setting it up is messy. And we have two integrals to evaluate. So with Cartesian coordinates, it seems to me that this integral is possible, but will take a fair bit of work. Still, I hope that it was helpful for you to see how we could set up this integral. Let's try it with other coordinate systems. Looking at our picture, we see that it has both a sphere and a cylinder. So both spherical and cylindrical coordinates seem promising. Let's try it with cylindrical coordinates next. Looking again at the xy plane, we saw that the region was an annulus, or a ring, a region between two circles. And this has a great description in polar or cylindrical coordinates. It's that the radius ranges from 1 to √3, and the angle theta ranges from 0 to 2 pi. Because we're going all the way around this ring. We're not just going halfway or a quarter of the way or anything like that. And our inside radius was 1 and our outside radius was √3. That's giving us the interval for r. For the z interval, z is greater or equal 0 because we're cutting off the xy plane and going up from there. And we're going up until we get to the surface of the sphere. It's bounded above by x squared plus y squared plus z squared equals 3. We can write that as r squared plus z squared equals 3. And we can make that z equals square root 3 minus r squared. It would be plus or minus square root, but we're looking at the top half of the sphere, so we'll take plus square root. And that's the upper bound. We want z to be less or equal to that. So our interval for z is from 0 to square root of 3 minus r squared. Well, that square root symbol a little bit cut away from me. There. So putting it together, the volume would be integral theta equals 0 to 2 pi, r equals 1 to square root 3, z equals 0 to square root 3 minus r squared. That is describing the region D. 1, because we want volume. So for volume, we integrate the function 1. And then we have to put the volume element. And this has this extra factor of r for cylindrical or polar coordinates. There's an extra factor of r that appears in the volume element. I have dz inside, dr next, and d theta on the outside. So our volume element has a factor of r. Don't forget the r. All right, this integral looks much better than the Cartesian one. I hope you'll agree. Let's go ahead and evaluate it. It won't be difficult. So, well, let's observe that this is in fact a separable integral. And that means that it's equal to the integral for theta from 0 to 2 pi of 1 d theta times the integral for r from 1 to √3 of r dr times the integral It's not separable. I'm sorry. It's not separable. Okay. The function that appears here is a product of a function of theta, namely 1, times a function of z, namely 1, times a function of r, namely r. And that's one of the things you need to have a separable integral. And the other thing you need is that the lower and upper bounds of integration are supposed to be constants. And this one, square root 3 minus r squared, is not constant. And I wasn't paying close enough attention. So we met one of the requirements for being separable, but not the other requirement. So let's start over with that evaluation. Let's try that again. So to evaluate this, what do we have? An integral from theta is 0 to 2 pi. An integral from r is 1 to root 3. Our function was r. The integral with respect to z is just r times z, because r is just constant. So integral of a constant would be r times z. For z from 0 to square root 3 minus r squared, dr d theta. Okay, let's do a little algebra and subtraction. So I have r times square root 3 minus r squared minus r times 0. We had 3 integrals. We've done one of them. 1 down, 2 to go. Let's use a substitution. Let's use the substitution u equals 3 minus r squared. So du is minus 2r dr. Then the integral of square root 3 minus r squared r dr is the square root of u to the 1/2 times du over minus 2. So that would be minus 1/2 times u to the 3/2 over 3/2 plus c if you like. It's not going to matter in our next step. So really this is minus 1/3 when you simplify those fractions. And then we have 3 minus x squared, or r squared rather, to the 3/2 power. And sure, plus c. All right, so that's what we'll use for our integral. We have, still theta going from 0 to 2 pi, no change there. The antiderivative that we found is minus 1/3, 3 minus r squared to the 3/2. And it's from r equals 1 to square root 3. And it's inside an integral d theta. And that was us finding the antiderivative. Now we can plug in some values to this antiderivative and do a little bit of simplification. So 3 minus root 3 squared, and then subtract, so plus 1/3, 3 minus 1 squared to the 3/2. Now 3 minus root 3 squared is 3 minus 3. So this whole term is 0. And here I have 3 minus 1. That makes 2. So we have integral theta equals 0 to 2 pi, 2 to the 3/2 over 3 d theta. That's a constant. So when we integrate a constant, let's cut to the chase. You just have the value of that constant times the length of the interval that it's being integrated over. We can't do a whole lot to simplify this. We could do 2 to the 3 halves is 2 times root 2. So we could say this is 4 pi root 2 over 3. And that's the volume of the region D. Let's play around with this and see if we could find it differently. For practice purposes, we have found the volume of region D. If that was our goal, then we're done. Really, our goal is to learn how to use cylindrical and spherical coordinates and to practice with them. So let's just try some variations on this approach. So let's try cylindrical again. In a different order. So last time we started with the XY plane, and the last thing we did was for any point in the XY plane or r and theta, the last thing we did was we looked at what was the Z interval. This time, let's try having Z first. So in our region D, let's start by choosing a Z value. And remember, we found that this went from 0 to root 2. So let's start with a Z value and then see what happens at that height. So let's use another color here. Well, at that height, it looks like we have a disc-shaped region coming from the sphere, but with a hole punched out of it from this cylinder. So on that plane, we'll have a disc-shaped region with a hole punched out of it. We know the radius of the hole. It's 1. That's a radius 1 circle. That's a hole in the middle because that's the radius of the cylinder and it's the same all the way up and down. But this radius of the larger circle at height Z, we have to figure that out. To figure that out, let's go back to the side view. This is part of the game. We look at the side view, the top view, the side view again, the top view again. We go back and forth. So our side view is a semicircle of radius square root 3. We are sitting at height C, and what we're asking for is the radius of the circle from the center out to the edge of the sphere at that height, cutting it off horizontally that height. Here's cutting off the sphere horizontally that height, and then going from the center out to the edge of it. So that distance is the distance we're looking for. Well, we know one side here, we're looking for another, and fortunately we know one more side of a triangle because we know this is a sphere of radius root 3. And it's a right triangle. So with Pythagoras or Pythagorean theorem, we can find that this is square root 3 minus Z squared. This radius here turns out to be square root 3 minus Z squared because of the Pythagorean theorem applied to this triangle. With that, we can now describe this region in cylindrical coordinates or in Cartesian coordinates, but that will be a little bit of a mess. So let's not try to do Cartesian coordinates. It's an interesting challenge if you want to try that. No. In cylindrical coordinates, this region will be described by the angle theta goes from 0 to 2 pi, and the radius goes from 1 to square root 3 minus z squared. So our volume is an integral from z equals 1 to root 2, theta equals 0 to 2 pi, and r equals 1 to square root 3 minus z squared. R dr d theta dz. So that's our volume element with a factor of r that we don't want to forget. So we have managed to set up our integral in cylindrical coordinates with a different order of integration. The first integral that we did had dz on the inside. This time dz is on the outside. And you can see that the bounds of integration have changed a little bit. I'll leave it to you, the viewer, to evaluate this integral if you like. If anything, this is arguably simpler than the first one we did. I don't think you'll need to do even a substitution for this one. So I leave that for you. Let's proceed to spherical coordinates. Well, we have visibly a nice sphere here, so it looks promising. Certainly the theta goes from 0 to 2 pi because we're going all the way around in this direction. We're going all the way around the z-axis in this example. The phi value is going down to the equator. So the largest phi value that we hit is pi over 2 for the equator. But phi doesn't actually start at the North Pole. The North Pole direction is when phi equals 0, but that's not included. That part got drilled out. We really start here. At this angle, and then phi proceeds downwards until reaching pi over 2. Well, let's figure out that angle. To figure out that angle for phi, let's take a side view. We're interested in this angle between the North Pole and that line from the center to the corner. And what we know is that the cylinder has radius 1 and the sphere has radius square root 3. From that, we figured out that the height here was square root 2. and then now we can figure out our angle. So the angle we're interested in that I'm marking here is the same as this angle at the top of the triangle, and we have some choices. So for instance, we could say that the tangent of that angle is the ratio between the opposite side 1 and the adjacent side √2. So phi is arctangent of 1 over √2. Or we could talk about the arc cosine of √2 over √3, or however you like. So there's different ways to say this. But let's, for the sake of definiteness, let's just pick one, and let's just say arctangent of 1 over √2. Okay, so we've answered the question, what's the interval for phi? And now, what happens with rho? Well, on any given one of these lines, rho goes between the two marked points. So rho starts at 0 at the origin, and we're not including the first part because that's in the cylinder that got removed. So at some point, we cross the wall of the cylinder and it turns on, and we start including those points until we get to the sphere. We know the end point. The end point is at radius √3 because it's a sphere of radius √3. But what's this rho value where it crosses the wall of the cylinder? Let's draw one more side diagram, a side view diagram. So there's a cylinder of radius 1. We're at some angle phi from the vertical, and we're asking for the distance that I'll mark in pink. We're asking for that distance. So to figure this out, well, observe that the angle phi marked here is the same as this angle phi. That is also phi. So we have a triangle here with an angle phi. It's a right triangle. The side across from phi has length 1, and we're asking for the length of the hypotenuse. In this triangle, the sine of that angle is the ratio between the length of the opposite side and the length of the hypotenuse. So rho is 1 over the sine of phi. Okay, so rho ranges from 1 over the sine of phi to square root 3. And just to write down our description, D is the region where theta ranges from 0 to 2 pi. Phi ranges from the arctangent of 1 over √2 to pi over 2. And for each phi, rho ranges from 1 over sine phi to √3. And the volume of D is the integral over this region that we've described. a 1 for the volume that I won't write, and then the volume element, which you might remember is rho squared sine phi, and then the d's. So in this case, I've got d rho on the inside, d phi next, and d theta on the outside. So shall we start integrating? We have an integral from theta from 0 to 2 pi, and an integral of phi is arctangent of 1 over root 2 to pi over 2. The function rho squared sine phi, it's not difficult to find an antiderivative there, 1/3 rho cubed sine phi, where rho ranges from 1 over sine phi to root 3 d phi d theta. Let's go ahead and evaluate that at those endpoints. From 1/3, root 3 cubed is 3 root 3, and then minus 1 over sine cubed phi, sine phi, d phi d theta. And let's do a small simplification. Root 3 minus 1/3. 1 over sine is cosecant. And here I have cosecant squared of phi. Okay, there were 3 integrals, 1 down, 2 to go. I lost the factor of sine phi. Root 3 sine phi minus 1/3 cosecant squared phi. Okay, let's see, we have integral theta 0 to 2 pi. I have to integrate root 3 sine phi. That's just minus root 3 cosine phi. Now I have to integrate cosecant squared of phi. It's not always easy to remember these, but the antiderivative of cosecant squared is cotangent. Cotangent phi. There's a 1/3 as a constant multiple, and we put in a minus sign, which cancels the minus sign that was already there, plus. And then we're evaluating that at phi is arctangent of 1 over root 2 and pi over 2. You may not have the integral of cosecant squared memorized. That's fine. Nobody expects you to have it memorized. Just have an idea where to look it up if it ever crosses your path. Let's start evaluating. So if I put in phi equals pi over 2, well, we've come this far, let's just write it down. Cosine of pi over 2 is 0. What's cotangent of pi over 2? Well, it's 1 over the tangent of pi over 2, which means it's 1 over infinity. This is also 0. So far, just 0. Now, we have minus root 3 times cosine of arctangent of 1 over root 2. And then plus 1/3 cotangent of arctangent of 1 over root 2. And that's integrated d theta. All right, it's not so bad. The arctangent of 1 over root 2 is the angle that fits into this right triangle with 1 as the length of the opposite side and square root 2 as the length of the adjacent side. Examining this triangle with Pythagorean theorem, we find out that its hypotenuse has length square root 3. And so the cosine of that angle is the ratio of the length of the adjacent side with the length of the hypotenuse. And then what's the cotangent of the arctangent? Well, the cotangent of the arctangent of 1 over root 2, that means 1 over the tangent of the arctangent of 1 over root 2. The tangent of the arctangent, those are inverse functions and they cancel out. So you have 1 over root 2, and that means it's root 2. So now we know all the values in our integral. I have positive square root 3 times the fraction we found, root 2 over root 3. Now, this time I have minus 1/3 times the other value we found, which is root 2. And that's what we're integrating d theta. Well, it'll simplify a bit more. Root 2 minus the third root 2, or in other words, 2/3 root 2. Integrating a constant, we have that constant times the length of the interval over which it's integrated, 2 pi. And we end up with 4 pi root 2 over 3 as the value of the volume of D. If you remember from earlier in the video, that's the same value we got using cylindrical coordinates. That's good. I'm glad we got the same answer. If our goal had just been to find the volume of this region, I think in this example, cylindrical coordinates probably were easier than spherical coordinates. If it had not been volume, but instead find the total mass when it was given some density, or just integrate some given function over this region, well, it would have depended on what was the specific function. For some functions, cylindrical would have been easier, and for some functions, spherical would have been easier, just based on what the function is. In this case, for volume, cylindrical seemed easier. Nevertheless, I hope it was helpful for you to see how we can set it up with cylindrical and spherical coordinates. In closing, we did cylindrical twice with different orders, and I feel like we should at least take a look at a different order with spherical, even though I won't go through as much detail. So to set this up in spherical coordinates with a different order of integration, what would go into that, or what's possible? Well, we could try to set up a row interval first and then figure out phi. So we pick the absolute smallest row that we get is row equals 1. And the largest row that we get is root 3. So for any row in that interval from 1 to root 3, let's draw the corresponding shape. For that row, it looks like we're going all the way around the central column. So theta goes from 0 to 2 pi. Looks like the colors have changed here, so let's change them back. The tricky part is going to be finding out the values of phi on this red sphere. Well, phi doesn't start at 0, and it doesn't go to the corner that we looked at before. Instead, it goes to this corner and then proceeds until it reaches pi over 2. So we have a small problem to figure out that starting angle for phi. If we take a side view, and I'll work this out, and that'll be our stopping point. In the side view, it's a semicircle of radius rho. And inside there, we've drilled a cylinder of radius 1, cylindrical of radius 1. So we're interested in this angle phi, which is the same as the inside angle at the top of this triangle. So looking at that, we can find that this angle is the arc sine of 1 over rho. So that gives the angle, the interval for phi. Now, with this interval for rho, theta, and phi, we can set up the integral. And I encourage you to try writing it down and see what would go into evaluating it. You might find that it's actually easier to evaluate than the one we worked out. So somehow in making this video, I've not necessarily chosen the easiest orders of integration. But I hope that seeing how we set up these integrals and how we work out the bounds of integration has been helpful. Thanks for watching. Bye.